Right, magnets. We have 3 toy trucks as part of a train, and each one has a magnet on the end. So at the moment, the way it's lined up, as you know, magnets, north attracts south. So we've got a south and a north next to each other, there and there. These are all 3 going to be attracted together, and when you pull it, it's going to move along all together nicely. And they want to know what happens if you take the middle one, swap it around and try and put it back in. So what happens if you try and put it in this way around with the north here and the south here? Okay, well, what's going to happen, now you have a south there trying to come together with a south right opposite it, so they're going to repel. Here you have a north up against a north, so they're going to repel. So it's going to be difficult to take this out, swap it around and put it back in. It's going to repel both of them. So that's the answer. The switched round truck repels the other 2, and that's answer D on your exam sheet. Simply because south repels south and north pole repels north pole. Okay, next bit. They show you a truck from above, and you have the magnet on each end like this. Okay, now they draw it with a little north there, and they put a south there, and a north there, and a south there. Why do they draw it like this? Okay, well, the reason is, with magnets, you can't have a north pole by itself. Okay, so if here's a magnet, you can't just write north pole, right? And you'll never get a situation like this. Same with south pole, you can't get a south pole by itself, right? If you're trying to draw 2 magnets and you see something like that, that's very wrong, okay? A magnet, any lump of magnetic material that's a magnet, it has to have a north pole and a south pole, okay? Which is why they've drawn an N and an S here. The magnet is that bit there, okay? Ignore this block in the middle as far as magnets go. The block in the middle, that's just a wood, okay? That's the magnet, which means there must be a north pole and a south pole. You couldn't have just a north pole on a magnet, all right? I cannot stress that enough. So that is wrong. You'd never see that. I keep banging on about this. A magnet has to have a north pole and a south pole, okay? So this end here of the magnet is the north pole. This end here is the south pole. That's why they've drawn an N and an S. That end's the north pole, that end's the south pole, okay? Which is why the way they drew the trucks and the way I've drawn them here for the first part is slightly misleading, okay? They've drawn just an N, but in reality, that end of the magnet would be the north pole and this end would be the south pole, okay? And here, in more detail, that end would be the south pole and that bit would be the north pole, all right? So, very important you understand that that is slightly misleading the way it's drawn. Magnets always have a north pole and a south pole. So that bit would be the north and that bit would be the south. That would be the south, that would be the north. That would be the north, that would be the south. That would be the south, and that bit, that end would be the north. Okay? That bit's the south, that's the north. That bit's the north, that's the south. Okay, I think I've stressed that enough. Let's get on with it. Right. The question is, what does the magnetic field look like inside the truck? Okay, let's do this in a different colour. Yellow. So, you've just got to know this. You've got to remember that outside magnets in air, okay, magnetic field lines go from north to south. Simple as that. So outside magnets outside the magnets, the field lines go from north to south. You've just got to know that, right? Now, remember, this whole thing is not a magnet. It's easy to get tricked because, you know, you're used to drawing a block and that whole thing is the magnet. But just that is the magnet. It's two magnets and that's the magnet, okay? Ignore these lines here. That's just wood. It's part of the truck. So, you've got a magnet here and a magnet here. It's like this, okay? It's like you've got a magnet there with a north pole and a south pole, and a magnet here with a north pole and a south pole. Okay, that's the situation. It's two magnets. Outside magnets, field lines go from north to south. Right, so got a north there and a south there. It's going to go straight across like that. And these bits are flat here, so we're going to have a region of constant magnetic field here. So draw another straight line there, and you're going to get another straight line there. Okay? It's just like as if you were drawing it two separate magnets like this. It goes from north to south. Okay? It's straight where the two magnets are flat. And then, I hope you've been drawing this at school, you should have been shown this. It curves slightly like that when you're beyond the flat bit. Okay, so it's going to look something like that. So, they shouldn't really be touching. I've been slightly sloppy there, but it's fine. Okay, they're not meant to touch. Yeah, irritated by that. No, I'm not having that. It's not good enough. Let's just correct that. Okay, they shouldn't touch. That's bad. That one's okay. We'll leave that one. Right. So that's north. There. Okay. Right. Goes like that. Right, so shouldn't really touch. Let's have it going just to about there. Slightly beyond. Okay, so there's a slight gap there. That one's fine. So it comes in there. Yeah. It has to join, they can't touch where they join. But at the same time, it can't be on the north side, okay? So I've got it right in the halfway mark there, so that's just acceptable, okay? It should probably join more like there. These things are important, okay? That's better. Okay. So that's what the magnetic field lines are going to look like inside the truck. It's just two magnets, right? So that is C, apparently, on the question sheet. Right. Yeah. So I'll just finish off by saying I said that outside magnets, the field lines go from north to south. What I mean by that is, well, what about inside magnets? Well, you're used to drawing stuff like this, right? You're given a north pole here and a south pole there, and you're told to draw the magnetic field lines. Well, outside the magnet, it leaves north, okay, like that, and it goes in at south. It goes, ooh, like that. See, outside the magnet, it goes from north to south, right? It's the so-called butterfly pattern. Outside it goes from north to south. But inside the magnet, it goes from south to north, right? Inside it goes like that. These lines join up there. Okay? So that's what the magnetic field looks like for a single magnet. And that's what it looks like in between two magnets. Here, got one there and one there, like this. Okay? So don't get the two of them confused. See, in air, outside the magnet, it's going from north to south. Outside goes from north to south. But inside the magnet, it goes from south to north. And you've just got to remember that, okay? And if you get a slightly tricky question where it looks misleading, you've got a block here, it looks like one magnet, but in fact it's two, just be careful, remember that, and you'll be fine. Okay, I'm going to rub out the board and we'll do the next bit. Okay, so what we've got now, the student keeps adding trucks to the end of the 3 trucks that she starts with, and each time she grabs the first truck, the trade engine if you like, and pulls the whole lot along at a constant velocity. And this is all going swimmingly until she gets to a total of 7 trucks, and then suddenly when she tries to pull it at constant velocity, the first truck, the one that she's holding, it always comes apart from the rest. So, explain why the train acts in this way by considering the forces involved. 2 marks. Mercifully, only 2 marks, okay? We can do that. Right. It's all about friction, okay? So, there's friction between each of the trucks and the railway. So every time you add another truck, the total resistive frictional force increases, and there too. Okay? So the total friction force increases when you add trucks. So you should say, as more trucks are added, total friction force increases. Okay? 1 mark, definitely. So the experimenter is pulling with a certain force, and that force has to overcome the frictional force. When it's traveling at constant velocity, the propulsive force, so let's say she's pulling with let's call it thrust. Okay? So we should say that the thrust or the pulling force, we'll call it thrust, it's fine, either is fine, right? So a constant velocity, the thrust equals the friction. The thrust force equals the friction force, okay? This is Newton's first law, okay? When the overall forces on an object are 0, then the object either remains stationary or keeps going at constant velocity. So we've got constant velocity in this case. So if this whole thing is to travel at constant velocity, the overall forces must be zero. If there's a frictional force in that direction, then it must have an equal and opposite force for the thrust in that direction. Okay? You can mention Newton's first law in this question if you like, no harm in doing that. So constant velocity, thrust equals friction, Newton 1, Newton's first law. Okay, so therefore, more trucks means more thrust. She has to pull with more force. Okay? The force between these magnets here is constant. Force between magnets is constant. Okay, and eventually the thrust required to pull this thing at constant velocity is greater than the magnetic force between these two trucks. Eventually the thrust is greater, thrust is greater than magnetic force and therefore comes apart. Make sense? That will definitely get you 2 marks. Okay, good. Right, next bit. Let's have a change of colour. Why not? Let's have green. Right. Devise an experiment to investigate the horizontal force needed to separate the trucks from the engine, like this. 3 marks. Right, it's a designing an experiment question. So at the end, we're definitely going to say repeat. Repeat the experiment at least, say 10 times. Okay. Right, so we've got to actually measure the force needed to separate the trucks. So, what piece of equipment do we use to measure force? It's a Newton meter, isn't it? Okay, so say that we're going to use a Newton meter and we're going to attach it horizontally between these trucks. So horizontal between the trucks. Okay? We are then going to pull like she did with constant velocity. Okay? And we're going to keep watching the Newton meter, and as soon as it comes apart, we're going to remember or record the maximum value that the force achieved on the Newton meter. In other words, the value of the Newton meter just before it came apart. So record the Newton meter force just before coming apart. Okay? And like I said, this is an experiment, so you always write this when you're describing an experiment. Repeat every time, okay? Marks for old rope, just say repeat 10 times, okay? Under the same conditions, okay? Repeat same conditions, take the remove anomalies, take the average of all 10, or 9 if you had one anomaly, of all 10 forces that you required. That's it. That will definitely get you 3 marks. Good. Third change of colour? No, it's a second change of colour, isn't it? It's a second change with a third colour. Okay. Explain why a larger force is needed to separate the trucks from the engine if the force is applied at an angle to the horizontal. Okay, so it's talking about, instead of applying the force in an exactly horizontal way like that, you're applying the thrust force at some funny angle. Okay? Right. Yeah, so some angle there. Explain why a larger force is needed to separate the trucks from the engine if the force is applied at an angle to the horizontal. Okay, I forgot to note how many marks this is worth. 2 marks, I think. Yes, it's 2 marks, I remember. Right. Okay. First thing to say, well, firstly, I'll draw a little diagram, okay? So, nothing wrong with the diagram, just a little diagram to show the examiner you know what you're doing. So from above, okay, it's an angle to the horizontal. The angle could be upwards or it could be to the side. So from above, you've got the thrust force to the side, let's say. That's fine, okay? So draw that and then draw a line here. Okay, and something like that, okay? So, what you're trying to show here is that if you're pulling, it's meant to be travelling in this direction, okay? So you've got the other things here, the other trucks. So it's going in that direction. If you're pulling with a thrust force at an angle like that, okay, this is the horizontal component of the force that you're applying. So that's the horizontal component of thrust. Good. Okay. Right, so first thing we're going to say is that only the horizontal component of the thrust that you're applying determines the force on the train. Okay, so only this thing here, that bit there, only the horizontal component determines the force on the train. Okay? That horizontal component is always smaller than the thrust. So the horizontal is always smaller than the thrust. Okay? So therefore, you have to pull with a greater force. Okay? Logical order of events, 2 marks. You can see that that arrow there is bigger than the component arrow. So the horizontal component is always smaller than the actual thrust. Or a slightly different way of looking at it, if you like, if you want to pull at a bigger angle to achieve that same horizontal component, the bigger angle, you have to have a bigger thrust still. See, that thrust arrow is bigger to achieve the same horizontal component. Make sense? Good. Okay. Anything else to say? No. We've smashed it. Well, there you go. Forces, friction, magnets. Done.